My name is Carol McCartney, and I am a geologist, and I am the outreach manager at the Wisconsin Geological and Natural History Survey in the UW-Madison Division of Extension. On behalf of the UW-Madison Biotechnology Center, the UW-Madison Division of Extension, Wisconsin Public Television, the UW-Madison Science Alliance, and the Wisconsin Alumni Association, thanks for coming out to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce my colleague, Esther Kingsbury Stewart. Esther Stewart's a geologist at the Wisconsin Geological Survey, where she specializes in understanding Wisconsin's oldest rocks, those that formed during the Precambrian time, generally about 800 million years ago. She has served as the Precambrian geologist for the Wisconsin Geological Survey since 2013. Prior to that, Esther worked as a petroleum geologist for several years in Texas. Esther was born in Massachusetts. She went to high school in Walpole, Mass., and she got her bachelor's degree from Mount Holyoke College. After she earned her master's degree from Idaho State, Esther worked in Houston, Texas. And in 2013, the survey was lucky enough to lure her away from the oil patch. At the survey, Esther collaborates with colleagues from UW-Madison, Parkside, and Baraboo, as well as the University of Minnesota and the U.S. Geological Survey. She's mapping our oldest and most deeply buried rocks using the latest geologic methods to bring new meaning to some long-lost data. It's an exciting story. Tonight, she'll tell us about reading the Deep Time Sedimentary Record, and I'll let her get started. Ladies and gentlemen, please join me in welcoming Esther Kingsbury Stewart.
Thank you. Can you hear me okay? Okay. Thank you, Carol. As Carol mentioned, the topic of my talk is the Precambrian geology of southern Wisconsin, specifically focusing on the area of the Baraboo Hills. So the title of my talk is a little more complicated than that. Reading the Deep Time Sedimentary Record, Historic Mine Records and Outcrops Preserved, a History of Ancient Rivers, Oceans, and Faulting in Wisconsin. So I hope in the next few slides to describe what I mean by deep time and sedimentary record, and to paint a picture of the geology of this part of the state, to touch on why it's so fascinating from a scientific standpoint and from the standpoint of understanding Earth history, and why somebody who's a citizen of Wisconsin might care. Why am I doing this as an employee of UW Extension? So this picture is a picture taken from the West Bluff, looking northeast towards Devil's Lake, if you've ever been to Devil's Lake State Park. So the ridges here are talus slopes that are underlain by Precambrian rock called quartzite. It's a very hard, durable rock. This is the Baraboo quartzite. That underlies this high topography here, the high topography here, and this rock here. Superimposed on this very old Precambrian geology is a much younger Quaternary geology, and I'll touch on that a little bit because it impacts the landscape and it impacts how I look and try to understand the older Precambrian geology, but the focus is really the older rocks. Before I continue, I'd like to acknowledge some of my collaborators. Letitia Brengham is a professor at University of Minnesota Duluth. She's doing some exciting work understanding banded iron formation, which is a kind of Precambrian rock. And then Eric Stewart from UW Baraboo is collaborating on understanding the structural interpretation. All right, so the title of my talk mentioned deep time. What is deep time? Deep time refers to the history before humans. So how can we understand what happened on Earth before there were written records? The clues are in the rocks, and in order to talk about that history, geologists use the geologic time scale. So this is a very simplified version of the geologic time scale. Geologists use a lot of big vocabulary words. I'll touch on these a little bit. They're not so important. Precambrian time is this beige color here. Precambrian just means before the Cambrian time, Precambrian, that's all it means. And then these are broken out into Paleozoic, Mesozoic, and Cenozoic, so ancient life, middle life, and more recent life. And then I'd like to point out the time scale starts here at 4,400,000,000 years ago, and it goes all the way up to today, to 0. So this is an incredibly long amount of time. It's really difficult to really understand what that amount of time means and think about the uncertainty involved in the interpretations for trying to unravel all of the events that happened over that time span. So this is the very simplified, complete geologic timescale. Over here is the geologic timescale, but only showing those rocks that are present in Wisconsin. So right away you notice that there are a lot of gaps in this timescale. There's an interval of Precambrian rocks, then there's a gap, then there are some Paleozoic rocks, and then there's a big gap, and then there are some Cenozoic material. So this is the time that I'm focused on and that I'll focus on in this talk. These rocks here are significant because they make up the groundwater system in Wisconsin. They're important for understanding our groundwater resources. And then, of course, the Cenozoic time refers to the glacial history. So that's all the material that was brought into this area during the last ice age. So I'll touch a little bit on how that's reflected in the landscape. The next important thing to understand or to think about as you think about the regional geology is the spatial distribution of the rocks. And so geologists communicate that through geologic maps. This is a very simplified geologic map of Wisconsin. The different colors represent different aged rocks. So if I'm teaching a very general audience, I give the analogy of a cake. So if you picture this as a cake shaped like Wisconsin, the brown part, that's the oldest Precambrian part, that's the cake. And then the Paleozoic rocks, these blue colors, that's the frosting. But the cake is a little bit slumped, and the frosting doesn't cover the entire cake. Part of the cake bulges up here in northern Wisconsin. The frosting, these Paleozoic rocks, are more flat-lying in the west. And then something happened over here, and they're really dipping quite steeply underneath Lake Michigan. So that helps communicate the three-dimensionality that is necessary for thinking about geology and geologic time. The area that I'm focusing on, again, is this area in south central Wisconsin. This canoe shape represents the Baraboo Hills. So if you're familiar with the Baraboo Hills, there's a south range and a north range. So here's the south range, here's the north range. To help visualize what's happening in 3 dimensions, it's often convenient to use your hands. So if you imagine that these rocks were once flat and then they folded, and you're looking down at a fold, you would be looking at a canoe shape. So that's what you're looking at when you are in an airplane, or imagine flying over the Baraboo Hills. You look down and see a canoe shape, you're looking at a big fold. And I'll talk about that a little bit more. All right, but it's a little more complicated than just that. As I mentioned, this whole, or most of Wisconsin was covered by glaciers in the last ice age, and the glaciers really modified the landscape and really impact the way that the land is expressed and used today. So the green color represents those areas that were glaciated during the last ice age. This cartoon here depicts the extent of where the glaciers were. And the thing to notice, so here's this driftless area, was not glaciated. So the landscape, I'll show some surface topography in the next slide. The landscape in the driftless area is quite different than the landscape in the glaciated area. The boundary right here cuts across the eastern nose of the Baraboo Hills, and I'll point that out. That's kind of fascinating. You can go to the Baraboo Hills, go to the state park, and you can see the moraine, the edge of where the ice went, the furthest extent of where the ice was, cutting across the park there. So this is a map showing the surface topography of Wisconsin. It's colored to represent elevation, so the higher colors are in the lighter beige colors and this brown color. The lower colors are shown in greens. So the first thing to notice very broadly, there's a dome here. This is the Wisconsin Dome. It's underlain mostly by Precambrian rocks. If you are familiar with Gogebic taconite, that was a relatively recent effort to mine iron. That was from this part of the world. This is also where the volcanic massive sulfide, so metallic mineral deposits, are housed in these rocks. The area that I'm focused on is down here. The Precambrian geology of this area is buried a little bit more deeply, and therefore there are much fewer hard samples of that material, so it's harder to understand and unravel that history. However, if you look here, there's that canoe shape. That's the Baraboo Hills. So there's a little ellipse of Precambrian rocks exposed at the surface. As you go to the east, there are little isolated places where Precambrian rocks are exposed or very close to the surface. But for the most part, that Precambrian surface dives into the subsurface and is covered by the Paleozoic rocks, the frosting in that geologic map cartoon. So what I'm hoping to do with my research is understand the Precambrian geology as it's exposed in the Baraboo Hills in order to understand what is happening in the subsurface as you go east across Columbia County and into Dodge County. And the practical application or the practical reason for that is the Precambrian rocks are an impermeable layer, or fairly impermeable layer, that forms the base of the Cambrian aquifer. So the Cambrian and Ordovician sediments overlie those rocks, overlie the Precambrian rocks as you go to the east in this area. The Cambrian rocks are the rocks that house the groundwater. If you understand the shape of the Precambrian surface, then you start to understand the nature of the overlying aquifer, and it's important for a practical reason. These rocks are also just really interesting, and I hope to talk about that a little bit too. Okay, so focusing on that area, again, this is a map showing the surface topography, and you can really see the canoe shape of the Baraboo Hills. So this is a fold of quartzite that is thought to be younger than 1,700 million years old. The constraint on that is not very good. It could be as young as 1,400 million years old, and some folks are thinking about that as a possibility right now. So it could be 1,700 million years old to 1,400 million years old. That's the uncertainty that we're dealing with. Okay, so in the next slide, I'm going to show a block diagram, so a cartoon in 3 dimensions that depicts a slice through this part of the Baraboo Hills. Before I do that, I talked about the glaciers a little bit. This is the moraine. See this linear feature? This is the moraine that was left behind at the greatest extent of ice during the last ice age. So this part of Wisconsin was glaciated. You can see these linear features are drumlins. This part was unglaciated. So this landscape is much more dissected. There are hills that are underlain by Paleozoic sandstone and carbonate that have been quite dissected by rivers over here. Okay, so if you took the eastern nose of that canoe and you tipped it on end, this is what you would see in a very generalized sense. So the Baraboo Hills are underlain by the Baraboo quartzite, a very, very hard rock. That's shown by this layer here. That was originally a sandstone, so it was deposited by rivers or in a beach as a flat layer. And then at some point in its history, that flat layer was folded into the canoe. So that's what you're seeing here. On top of the quartzite, there's a very interesting kind of rock called a banded iron formation. And I have samples of that, which I can show folks at the end of the talk. Iron formations are unique because they're not forming today. This is a rock type that only formed in the Precambrian. So geologists are very interested in looking at iron formation because they think that it tells something about the chemistry of the water that these rocks deposited in, and perhaps the atmosphere. It tells you about whether or not the water was oxygenated or anoxic. If there was, the rocks, I'll show some pictures. The rocks are essentially layers of chert, which is a very fine-grained quartz, and then layers of an iron-rich siliciclastic material. And that tells you something about fluctuations in the water chemistry. Okay. So the big question that I'm interested in is, what was the environment like 1,700,000,000 years ago, give or take a couple hundred million? So this is a picture of the Baraboo quartzite. You can see there's a change here. So this is a sandier, coarser grained sand, larger grain size. Here, these layers are original layering. These layers have not been overprinted by later deformation, which is pretty incredible if you think about it. They're representing the original dunes and laminations that were formed as the sediments were deposited in whatever environment they were depositing in. On top of this coarser grain layer is an interval of finer grain material. So this is still a sandstone, but it has a lot more siltier material in it. And if you look at the shape, you can see that it looks pretty crinkly. That's because this layer is preferentially accommodating the deformation that folded the Baraboo Hills. So all that deformation is being expressed in this finer grain layer as opposed to this coarse grain layer. I'll just point that out. So other folks have thought a lot about this. It's something that you can see at Van Hise Rock, for example, if you've ever been there. All right. I'd like to give some perspective, though, and really touch on geologic time. This is a little bit corny, but it really, I think, communicates just how long the Precambrian time is and the main events that led to evolution of animal life as we know it, which is one of the, how did animal life evolve? Why did it evolve? When it did is a fundamental research question that really drives a lot of research in the Precambrian. So if you think about the time scale is your arm, the beginning of Earth history is about at your armpit. Precambrian time, that's all time before the Cambrian time period, goes from your armpit to the evolution of animal life, which is about at the beginning of your fingers. So this is the time period before animal life evolved. Land plants evolved at about your first knuckle. Dinosaurs evolved at about your second knuckle, and human evolution is represented by the white part of your fingernail. So I think that really puts things in perspective. Okay, so to run through some significant things that are going on in the Precambrian, the oldest microfossil evidence of life is way back here in the Archean. And there's evidence for cyanobacteria, which are photosynthesizing single-celled creatures. So if you have critters that are photosynthesizing, then you can start to create oxygen and add that to the ocean and the atmosphere. The earliest evidence for oxygen in the atmosphere is much, much later. Oxygen began to build up over a very long time period, and within that time period, the rocks in the Baraboo Hills were deposited. This is significant because, remember, there's an iron formation in the Baraboo Hills. The iron formations are unique because they may, and in fact a lot of people believe that they do, record this history of oxygenation of oceans in the atmosphere. The interesting thing, though, about the Baraboo rocks is that they're a little bit younger than most of the other banded iron formations. So that's an interesting problem. If you think that the banded iron formations stopped forming because suddenly the oceans were oxygenated and they couldn't form anymore, well then wait a minute, why are there some forming at 1,700,000,000 years ago and now we think perhaps these rocks are even younger, 1,400,000,000 years ago. That creates an interesting problem. All right, so this is a picture of Banded Iron Formation. It's a very striking rock. It's very pretty. The red layers are chert layers. That's microcrystalline quartz. That's silica and oxygen. It's a chemical sedimentary rock like a limestone, so it's a material that precipitated out of the water column as an ooze. Alternating between the chert layers are these hematite or magnetite-rich layers. Generally, they can have other minerals in them as well. So the key is you're going from layers with no iron in them to layers that are iron-rich. You're alternating back and forth. And so that's thought to represent fluctuations in the water chemistry between more oxygenated water and less oxygenated water. And then folks relate that to animal life and photosynthesis and stuff like that. All right. So why might we care about early Earth history, Precambrian Earth history? Folks use the Precambrian rock record on Earth as an analogy for what we might expect to see on Mars, for example, as we're exploring for life on Mars. All right, but I work for Extension. So why does the average Wisconsin citizen care? And I think the most practical or immediately practical reason is groundwater quantity and quality. So this is a picture of one of the folks that works at the survey working on a well. The well is a pipe in the ground. The water coming out of the well is groundwater. So you can stick a pipe in the ground. The water is housed between little particles in the rocks or fractures in the rocks, and you can pump it out to get drinking water. This is a cross-section from Dodge County. So this layer here is the Precambrian layer. The red line is the contact between the Precambrian and the overlying Paleozoic units, the Cambrian Ordovician aquifer rocks. So this is the base of the aquifer. This is the main aquifer unit, and all of these sticks are water wells that help constrain this interpretation. And so what I'm hoping to communicate with this picture is that and this is stretched 15 times, so it's really exaggerating the topography on that surface. What I'm trying to communicate today is that undulations on this surface are infilled by mostly the overlying Cambrian Elk Mound group. That's a sandstone that's a very good aquifer rock. And so if we can understand some of the characteristics of this Precambrian surface, then we can start to understand groundwater quantity, and I hope to show a little bit later on groundwater quality as well. All right, that's great, but how do you rewind time and understand what happened 1,600,000,700,000,000 years ago? So if you are aware of plate tectonics, the Earth's continents have drifted apart and drifted together several times over Earth history. This is a picture showing the breakup of a supercontinent called Nuna. This picture probably represents a time a little bit after deposition of the Baraboo quartzite. Wisconsin is somewhere up in here. The exact boundaries of this continent or the nature of how it grew and came apart is pretty hazy. There's not really good constraint on what happened. The general knowledge, though, is that this Laurentian craton, which is the backbone of North America, grew from north to south, present-day north to south, and the Baraboo rocks were deposited close to the edge of that continent when it was quite young. So they were underlain by a relatively young crust as the continent was growing. All right, so I'd like to take some time to show some pictures of what the rocks look like. When I first got to Wisconsin, I'm not from the Midwest. I hadn't ever been to the Baraboo Hills before, and my impression, my assumption was that it was just a boring purple quartzite. But it actually isn't. It has a lot of variability, which is significant for understanding the environment that these rocks formed in. So this is a picture from the very base of the Baraboo Quartzite. And when you look at it, you can see there are these lines like that, layers in the rock, and there are all these little spots in it. Those spots are rounded white quartz pebbles. So think about what kind of environment can transport fairly large quartz pebbles. It must have been a fairly strong current to be able to pick up that material and carry it. The other, I think, fascinating thing to point out is these layering represent bedding. So these are original sedimentary structures that formed as this rock was being deposited as sediments. They're compacted, but their shape is essentially a primary structure, which is pretty incredible after 1.5 billion years. This is another picture showing a layer of quartz pebbles in a more medium-grained sandstone. So there might be a few floating pebbles in this interval and in this interval. Most of the pebbles are concentrated perhaps as a lag or over a scour along this bedding plane. In some places, there are outsized rounded quartz pebbles as much as 2.5 centimeters. There are some smaller quartz pebbles in this picture, and then this really big rounded quartz pebble. So what kind of environment can source and transport material like that? That's a question that I'm still thinking about. But most of the Baraboo Quartzite is not pebbly. Most of it tends to look like this. So there are larger layers here. There's a bedding surface, there's a bedding surface, there's a bedding surface. These are organized into beds from here to here. And then you can see there's finer cross beds within that are very laterally continuous. In other places, there are cross beds, that's what these lines are, that go in different directions. So these are, folks can measure these and understand current direction. If you can get a good measurement, you can start to plot current direction and get an idea of if you think this is a river, the direction that the river was flowing. If you think this was a beach, the direction that the waves were coming in and out. And then there are features like this. So this looks like a big scour surface, perhaps the base of a big channel. And then this picture that I've shown before, where there are variations in grain size, broad cross bedding here, finer grain material here. And then if you've been to the Baraboo Hills, you've probably seen rippled surfaces. So this is looking down at the top of a bed. These are fossils of ripples on the top of the bed, which is pretty incredible that you can preserve ripple marks, billion-year-old ripple marks. So that tells you something about the energy of the water and perhaps the setting, if you can link it with other pieces of evidence. In addition to these primary sedimentary structures, there's also a lot of deformation, which is what I'm showing in this picture. So the picture on this side shows quartzite that has been fractured or has a very strong cleavage in this orientation. So that I can't see any evidence of primary structures in this. This is all secondary deformation. Deformation is a little bit more obvious in this picture. These are angular clasts of quartzite within a quartz matrix. So it looks like the quartzite broke into pieces. The pieces didn't move very far. They were perhaps carried within a quartz-rich solution that precipitated out quartz. So how did that happen? Through the process of mapping these rocks, we discovered a fault in the south range of the Baraboo Hills. This is the damage zone of that fault. It's a pretty big structure. This is a wall of really ugly-looking rock. It's kind of associated. It's in close proximity to this picture. that is associated with an offset in layers that we're mapping. I'll talk about that a little bit more. So that there are both primary structures and secondary deformational structures preserved in these rocks. This is a picture showing evidence for fluid flow. This is purple quartzite. These are probably primary crossbeds here. And then there's this boundary that cross-cuts what are probably primary sedimentary structures. The rock here is white. The rock here on the outside is pink. So that's evidence for fluid that flowed through the material, at the sandstone after it had been deposited, and bleached it. This is a close-up of a quartzite that's probably been altered by fluid flow and bleaching. Okay, so moving up the stratigraphic section, so up the layering of rocks into slightly younger rocks, the lowest layer are the Baraboo quartzite. Those are all the pictures that I just showed you. On top of that, in the center of the syncline, are shales and iron formation. These rocks are only present in the subsurface. They're not exposed at the surface. So we only know about them from, actually from mineral exploration and mining that happened in the Baraboo Hills in the 1900s, around 1903. So these are pictures of drill core that were collected with steam-powered drill engines about 1903. These drill core are saved at the core repository at the Wisconsin Geological and Natural History Survey. The first picture here is a gray slate called the Sealy slate. And then above the Sealy slate is the iron formation. So you can see a little bit of red. It's a dolomite or a limestone, and then iron-rich siliciclastic rock. These pictures over here are also pictures of the iron formation drill core. And in this case, I've cut the drill core in half, so you're looking at a scan of a cut face of the drill core. And that really brings out some of the texture in that rock. It's really very pretty. So there's granular textures in some intervals. Most of the rock has these fine laminations, this fine layering. And this picture shows some, the swirled appearance is probably soft sediment deformation. All right. So the Baraboo Hills have been the focus of work for over a century. How can we add to that incredible body of work? And in fact, folks from the University of Madison, Gordon Medeiros and Bob Dott, are the two folks that I'm most familiar with, have done a lot of work to understand this area. They've really advanced what we know about the Baraboo Hills. So how can we add to that? This is a picture from Dial and Dott's 1970 geologic map of the Baraboo Hills. This is a very well-known publication that's used by universities, Midwestern universities that visit the Baraboo Hills quite frequently. So we thought about what are some of the outstanding questions that would really help understand the regional Precambrian geology. So not just the geology in the Baraboo Hills, but the geology, the Precambrian geology underneath Columbia County and Dodge County as you go east. And one of those outstanding questions is there a younger quartzite on top of this iron formation? Is the story a little bit more complicated? So the idea that I'm trying to test and that I'm hoping to explain in the next few slides is that there's a Baraboo quartzite, an iron formation on top of that, and then a younger quartzite. So I'll talk a little bit about how I went after that question. All right. So folks have suggested that there is a younger quartzite called the Dake quartzite for a long time. And there's been kind of it's been interesting to look at the literature and look how opinions have changed through time as access to the primary material, the mine records and the core data what became less accessible, opinions changed. So in 1935, Andrew Leith defined the Dake quartzite and an overlying Sealy slate. He recognized that they existed and defined them. Wenberg in 1936 wrote, unconformably above this lower Baraboo series lies an upper Baraboo series consisting of the Dake Quartzite and the Rowley Creek Slate. But then World War II happened. Andrew Leith left the University of Wisconsin, moved to Washington, D.C. C.K. Leith, who also worked on this on the Baraboo Hills, retired. All the students that were working with Andrew Leith, there were a lot of students working with Andrew Leith to map the Baraboo Hills, and that effort stopped. Then in 1951, a fellow named Schmidt did his master's thesis at the University of Wisconsin on the Dake Quartzite, looking at the old mining records. He proposed that the Dake Quartzite, its existence has been questioned by many, including the author. He suggests instead that faulting in a step-like fashion has brought the lower Baraboo Quartzite to the surface in several places. So instead of having a younger quartzite, he's arguing that faults carried the older quartzite up to the surface, and that's really what we're seeing. In 1970, Dial and Dott wrote, there is no strong reason for believing that the Dake Quartzite, if it exists, does indeed crop out. In 1990, Clayton and Attic wrote, the Dake problem cannot be resolved presently with the available information. So by this time, the cores had been lost, or the core records stored in the basement of the Geological Survey, and they were not very accessible. Then in 2016, Bjorn wrote further evidence for their existence, meaning the Dake Quartzite has been elusive, and they probably represent a structural repetition of the Baraboo Quartzite and Sealy Slate. So that's the evolution of thought on the stratigraphy in the area. But not all the drill cores or drill logs were lost. Not all the drill logs were lost. This is a picture showing LIDAR, so that's the surface topography of the Baraboo Hills. This is the south range of the Baraboo Hills coming around like that, the eastern nose, and then the north range. This is the Johnstown Moraine cutting through the eastern part of the Baraboo Hills. And superimposed on that are scanned images of historic mineral exploration maps. These maps show the location of properties. Many of the same families still live in the area and own the same properties, which is incredible. And they also show the location of wells, which I've digitized and are shown by these dots on the map. So we are able to catalog the spatial distribution of some of the data. Incredibly, not all the cores were lost either. So about maybe 10 years ago now, the survey got a phone call from a property owner who had an old shed on their property with trays of core, and they wondered if we wanted it. So, Bill Batten and Bruce Brown took the talk about backing the survey's 10-foot trailer down like a 3-mile dirt driveway and collecting this stuff. And they brought it back to the survey, and it sat in the core repository for almost a decade. Then, when I started, several folks were retiring and cleaning up their offices, and there was a big effort, there's still an ongoing effort, to catalog and reorganize some of this old data. So there was a drawer in the basement with my name on it, and I would go down and look at it and not really understand what I was looking at, and then suddenly realized that some of these old records were actually maps that showed the location of some of those cores. So now we could tie these cores, these mystery cores, to a location and start to map the geology, understand the spatial distribution of some of those buried Precambrian rocks. So this is I've digitized over one of those old cross sections. And what I want to point out here, the purple layer is the iron formation. The top of the iron formation is a carbonate rock. On top of that is shown a quartzite. So these are the drill holes. Those are the control points. So this drill hole encountered quartzite and slate over dolomite, as did this one. And these are quite thick. This is like 200 feet plus. So I'm fairly confident that they got that right. it thins quite a bit to the side. The other thing to notice is the shape of this contact. While it's folded, it's not quite as folded as the underlying units, which tells you something about the relationship between deposition and folding, the timing of deposition and folding. All right, so that was in the eastern Baraboo Hills. In the western Baraboo Hills, we had all these maps, which folks have known about for a while. What hadn't been done was nobody had gone through all of the drill logs, cataloged what the top Precambrian unit was, and plotted that top Precambrian unit on a map. So that's what I'm hoping to show here. The different dots represent the top Precambrian unit in each drill hole, shown up by a point. So the Baraboo quartzite is in blue, and it really helps to use your hands when I talk about this to help visualize in 3D. So the Baraboo quartzite is the oldest, that's in the blue dot. Over top of the Baraboo quartzite is the Sealy slate, that's shown in the black dots. So if I'm going to draw a contact between the Baraboo quartzite and the Sealy slate, I could draw it about there. Okay, on top of the Sealy slate is the Freedom Formation, that iron formation. The Freedom Formation has two main layers, a lower layer that's more iron-rich and an upper layer that's more carbonate-rich. So the lower Freedom Formation is shown by the red dots. So if I were to put a contact between the slate and the iron formation, I would draw it like that. And then the upper Freedom Formation is shown by the orange dots. So there's a contact separating the upper and lower Freedom Formation. Finally, there's an outcrop of quartzite that has been kind of debated whether it's Baraboo quartzite or Dake quartzite. It works quite nicely to have it be a younger unit. So if you think about, if you can visualize what I'm doing, if you have layers of rock or layers of paper and you fold them, the youngest layers are going to be bent down along the axis of that fold, and the older layers are going to be expressed along the outside of the fold. So that's what this map pattern is showing. It's suggesting that there is a younger quartzite. It's consistent, stratigraphically younger quartzite is consistent with the map pattern. All right, so we put this type of evidence together and made a map of the Precambrian geology of the Baraboo Hills. This is what it looks like. This light gray color is the Baraboo quartzite. There are a lot of outcrop measurements of bedding orientation, the strike and dip. And then this gray layer is the Sealy slate. The pink layer is the Freedom Formation, and the purple layer is the quartzite. This is a fault which we interpret as a thrust fault cutting across the northern part of the Baraboo Hills. This has been identified by other folks as well. All right, so we think that there's a young quartzite. So what? Who cares? One reason you might care, that these are a series of cross sections from the east to the west of the Baraboo Hills. All of these lines are drill hole control or well control, so they're pretty well constrained. From these cross sections, you start to get an idea about how the hardness of the different layers affects the topography on the Precambrian surface. So in this example, that hard quartzite is forming a resistant knob. The edges of that have been eroded and infilled by the overlying Cambrian sandstone. And I see similar evidence for similar things in Dodge County, where this yellow layer is the aquifer layer. All right. So we decided to try to push this a little bit further. As when we started out, we thought that we could just identify this pebbly layer that had been recognized by other folks at the base of the Baraboo quartzite, map that in 2 months and be done with it. But of course, it was more complicated than that. So what we ended up doing is detailed 1:24 scale mapping. So these are the 1:24 topographic maps, field mapping of the North Freedom Quad and the Baraboo Quad. Those are the two quads that contain the park, Devil's Lake State Park, and a lot of the Nature Conservancy land. So it was a lot of good exposure, and it was relatively easy to access a lot of the rocks. This is what one of the field maps looks like. So all of those marks are measurements of bedding orientation where we went and looked at the rocks, measured their orientation, and took a description. The goal is to try to break the Baraboo quartzite into mappable layers, and if you can map those layers around, you can identify places where they're offset by faults, which is what we're trying to do. And we were successful in doing that. This is a cartoon map of the two quads side by side. The different colors represent different map units. So yellow is Quaternary, this pink color is the Cambrian undivided. And then these greens and grays and purples represent members of the Baraboo quartzite that we've broken out in the field mapping. And one of the more significant discoveries is a fault shown by this dark black line that cuts through the southern part of the Baraboo Hills. This is a cross section from B to B prime, showing how the layers of quartzite, which are shown by these the different colors, are bent into the syncline, so that fold that makes up the Baraboo Hills. And then in the very broad southern range of the Baraboo Hills, there are these little secondary folds, and this fault right here is shown right here. All right, so we identified a fault. Who cares about that? We're not the first person to identify faults in the South Range. This is an unpublished map by Andrew Leith, and he's showing a fault in about not exactly the same area, but in a similar area in orientation. We went to that area. We haven't mapped it in detail, but we did find outcrops of the overlying Cambrian rocks. These are the rocks that make up the aquifer elsewhere, that were quite fractured. So the layers of the rocks go like this. Those are the original depositional layers in the rocks. And then there's this fracturing that cuts the rocks at a high angle. So this isn't typical. Generally, the Cambrian rocks don't have these big fractures. We hypothesize that the fractures are here due to reactivation during the Paleozoic of these older Precambrian structures. And so that becomes important for understanding groundwater quality, where these rocks make up the aquifer. All right, so how do we make that leap? Well, based on some evidence which I haven't touched on at all, we think that the Baraboo quartzite deposited in a series of en-echelon fault-bounded basins. This fault cuts through Columbia County, northeast Dodge County, and into Fond du Lac County. I'm working on a related project to map the bedrock geology in Dodge County. As part of that effort, we've been fortunate to collect drill core of the Paleozoic section. So these are two examples of drill core from Dodge County in the Cambrian sandstone. The sandstone is the white, the quartz greens are the white part. Notice all the gray. The gray is sulfide mineralization, probably related to the lead zinc district in southwestern Wisconsin. So the same fluids or events that created the lead zinc district also impacted much of southern Wisconsin. And the evidence are these sulfide minerals in the Cambrian rocks. While these are not in any quantity great enough to represent economic deposits, they could and likely do impact groundwater quality. So that's an avenue that I'm interested in pursuing. We notice if we plot detectable arsenic is an accessory element associated with this sulfide mineralization. If we query some of the groundwater or the well water data, I think that we're starting to see a correlation between proximity to some of these folds in the bedrock and presence of detectable arsenic. So that's something that we're trying to understand a little bit more. It's just in its infancy as an idea. So to wrap up, I wanted to just talk a little bit about the value of the survey. This is a picture of some of those old those old core, what they looked like when we picked them up about 10 years ago. This is the core of the iron formation from the early 1900s. So they were stored in 10-foot long wooden boxes. And they were pretty disgusting. They were covered in mouse poop. They'd been sitting in a shed for over 100 years. And there was pressure from time to time to throw this out. We didn't know where they were located. They were disgusting. They didn't look, they're small diameter. They're hard to look at. So why bother storing them in the facility? They're taking up space. But these are priceless for understanding the history of the geology. We have the historic documents at the survey through the hard work of folks combing through those and realizing that they're important, cataloging them and saving them, and then folks from the survey going and getting this, saving this from being thrown out and storing it, and then the effort to link those two together, that old information that we would be impossible to collect today, we're able to access and rediscover, which I think is a pretty interesting story in itself. So with that, that's my story, and I can take questions.